In this video, we're going to talk about the addition of radicals to an alkene. Okay, so everything we've talked about up until now is talking about alkanes. Talk briefly about radicals and alkenes, and then talk for a little bit about the stereochem of radical reactions, which I know every time you hear stereochemistry, shudder a little bit, but it's really not bad at all for radical reactions. So what happens when we have a radical with an alkene? And this is something that I really want you to know from chapter 12. Be on the lookout for it, called the peroxide effect. The reaction that's on top here, we've seen this already. This is an old reaction of an alkene, right? The alkene plus a hydrogen halide. We would be able to predict from chapter 6 that that reaction makes 2 bromobutane following Zaitsev's rule. Okay, or sorry, that's Markovnikov. Right? But if we do the same, jump to slide there. If we do the same reaction, exact same reactants plus peroxide, right? Addition of a hydrogen halide in the addition of peroxide, notice the product is flipped where the hydrogen and the bromine went. Okay? Because in the presence of peroxide, bromine is the electrophile. Okay, so we still end up following Markovnikov there, but as we see at the mechanism, it's a totally different way to get there. In this type of reaction, the addition of a hydrogen halide to an alkene in the presence of peroxide is the only way to synthesize primary alkyl halides like this. So let's see how it happens. Okay. Well, obviously, we have to have something to start this off. Being a radical mechanism, we need some sort of radical initiation, right? And that has to come from the peroxide. So we have our peroxide with heat or light, and that results in homolysis of the oxygen-oxygen bond there, right? A homolytic bond cleavage because of that weak bond. Oxygen-oxygen bonds aren't all that stable. So that's the initiation that gets us our radical. Okay? It's called an alkoxy radical in solution. Okay? Oxygen there is going to complete its octet by pulling hydrogen off of the hydrogen halide, HBr in this case. Okay? Now, this is still technically, you see it's labeled here as an initiation step, right? Because it forms the radical that's first used in the propagation step. Okay. And then once we have that, right, we see we're going radical to radical, radical to radical. These are our propagation steps, which is driving forward, right? Bromine here also wants to complete its octet, right? And it does so by pulling an electron from the weakest bond in solution, which is now the pi bond here. Yeah, that's the weakest bond, which previously has caused it to act as a nucleophile. Now it's causing us to react with my radical. Okay? So we break the pi bond. Again, it's a homolytic cleavage. That causes bromine to fill its octet and to simultaneously bond to carbon there. Okay? And we formed another radical reaction. Okay, so notice here, right, bromine is adding to the carbon with more hydrogen because that forms the more stable secondary radical in this situation. That's why we end up getting a primary bromide. Okay, then that radical pulls off another hydrogen, and then this is going to form a bromine radical to again jump back forward, and we see why this is a propagation and a radical chain reaction. With those radicals in solution, we have 3 possible termination steps, right? You could have your bromine radicals coming together to form Br2. You have your bromine radical coming together with your alkyl radical there to form a dibromide. Okay? Or we could have 2 of these guys coming together to form a big side product there. So again, we see that it's not entirely selective. No radical reaction is, but again, it's the only way to form a primary bromide. Okay? It's a radical addition reaction because bromine has added to our product addition via a radical mechanism. Okay? It needs a radical initiator in order to occur, and peroxide is the initiator in this case. Okay? That causes bromine to be the electrophile. So we're not violating Markovnikov, we just switched who's acting as the electrophile. Okay? So definitely know, right, that the fact of peroxide there is going to change your product. Know that bit of information and be able to know the mechanism for a test as well. Okay? The advantage, right, mechanism is certainly a little more complex, Okay, but if we were doing HBr and no peroxide, you would have to worry about carbocation rearrangement. And as we mentioned in an earlier video, right, radicals don't rearrange, so you don't have to worry about that. If they did, we would never be able to synthesize a primary alkyl halide. Okay. And the other thing that's nice, right, it's a bummer that you've got one more thing to worry about, right? Previously, you knew those reactants and how they went together, but now I throw peroxide in there and it changes things up. We only see the peroxide effect with bromine, okay? Now, previously, we could have done HCl or HI here. They don't undergo the peroxide effect, okay? Which is great, okay? Nothing extra to worry about there. You still get the same type of reaction that you would have gotten in the absence of peroxide, exactly what you would have predicted from chapter 6. And the reason for that, right, if we look at bromine, both of those reactions are exothermic, whereas with iodine or chlorine, you see that one of them is endothermic. Okay? So the fact that with bromine, both of the propagation steps are exothermic, that's kind of driving these things forward, right? It encourages propagation because your propagation reactions are always competing with your termination reactions. If termination happens too early, then it's not going to work, which is what we see with all of the other hydrogen halides. And termination is always exothermic because it's only forming bonds, which in itself is by definition an exothermic process. Okay? So in order to even be able to compete, everything has to be exothermic, which is why we only see the peroxide effect with bromine. Yep. HCl or HI, they just terminate, so no big deal. Know the peroxide effect, know what happens for HBr only, be able to predict the product, and know the mechanism by which it occurs. Big takeaway from chapter 12. Number 2, after predicting reaction yields. Yeah. What about stereochem of these reactions as promised? Well, the good news is there's no new rules to worry about. So we can predict a product. And we know that an alkane will react with bromine with heat or light to add bromine or chlorine. Okay. In doing so, that forms a new asymmetric center wherever your halogen went. Okay. But going from 0 asymmetric centers to 1 asymmetric centers, as we've seen in the past, just like with carbocations, when we form a new asymmetric center, 1, right, we get a racemic mixture. So you're going to get 50% R, 50% S. And the same thing happens when we do radical addition to an alkene, right? We see HBr here, the peroxide effect. We formed a new asymmetric center, but we went from 0 to 1, so we get a racemic mixture. And the reason for that is just like carbocations, which are sp2 hybridized and therefore trigonal planar, radicals have access to either side. Okay? So we go through our radical intermediate, whether we're adding bromine with an alkane or HBr with an alkene, we're again sp2 hybridized and planar. So it's just as probable for these things to approach from the top as for them to approach from the bottom. So we get 50% R, 50% S. Okay. Same thing right here, new reaction. Okay. If we pull a hydrogen off of an asymmetric center, as we see here, right, we took this hydrogen away, right, because it reacted with bromine to form HBr. It got plucked off there. We took this carbon, which is sp3 hybridized. Now it's sp2 hybridized. We replace it with a bromine in that situation, but notice now we get a mixture of enantiomers because you can think about this bromine from coming from the front or coming from behind. Okay, 50% chances of each, so we're going to get half of one enantiomer, half the other. 50% R, 50% S, right? Racemization. Nothing crazy to worry about. That's probably the best part of chapter 12. You always get a racemic mixture for these bad boys. So that's it, right? That's nothing to stress out about from chapter 12. The big thing to know from this video, the peroxide effect, right? Predicting the product and knowing the mechanism by which you get there, the initiation step, the propagation steps, and the termination steps.